tissue last time. We talked about what makes up a bone is collagen fibers and then hydroxyapatite crystal, which gives bone its hardness. But the arrangement of bone, even though all bone is made of those things, collagen fibers and hydroxyapatite that's created by osteoblasts, which become osteocytes that essentially are cells that are embedded in bone that they made. Osteoclasts reabsorb bone, so they destroy the collagen fibers, they destroy that crystal. But bone comes in sort of two forms that have different characteristics. So compact bone is very, very dense. In other words, it's very strong. It's strong for its size, but it's heavy. And compact bone evolved to conduct forces in just one direction. So, like in the diaphysis, the shaft part of a long bone, that's where you're going to find a lot of compact bone because essentially all those forces are going from the top to the bottom sort of in parallel. The other kind of bone is spongy bone. Spongy bone is also called cancellous bone. C-A-N-C-E. Here, I'll just write it. Cancellous. Because your book sometimes talks about it like that. It's an older term, but spongy bone is also called cancellous bone. Spongy bone. It's cancellous bone. Not bone. All right. So we're going to talk about each of these different kinds of bone in turn. But this spongy bone or cancellous bone, unlike compact bone, which is very dense and strong but heavy, spongy bone is much more lightweight, and it evolved to conduct forces that are arriving in multiple directions. So in the epiphyses of a long bone, the knobby part at the top and bottom, we find a lot of spongy bone because those forces are coming in, either in a curve or from multiple directions at once. Spongy bone is much more crushable than compact bone is, but it is lighter for its size than compact bone is. And all bones in the body have both types. So it's not like there are compact bones and there are spongy bones. There's compact bone and spongy bone in every individual bone, as we'll see more when we get to the when we start actually talking about the individual bones in our next unit together. So first up is compact bone. Compact bone is arranged in many ways like if you took a bunch of drinking straws and you held them all together, that's sort of like compact bone. That's sort of the way it works. Each one of those drinking straws is what we call an osteon. So the osteon is the functional unit of compact bone. So when I use this term functional unit, and we'll see that term throughout the course here, this is the smallest part that completes the primary function of whatever we're talking about. So for compact bone, what's its primary function? Well, it's to conduct forces in one direction, to be very dense and very strong. So the osteon is the smallest part of the bone that actually accomplishes that. And each one of these circles here, or tubes, like a drinking straw, each one of these is an osteon. So here's one, here's one, here's one. And if we look at it from the side, this whole long thing is all osteon. So if we take one of these osteons and we zoom in, what we see is that there's a canal in the middle called the central canal. Inside that central canal are vessels. So we've got an artery and a vein. Why? Because there are osteocytes that are in the walls here. Remember, in each one of these little spaces, these lacunae, there's an osteocyte. And those osteocytes are living cells. So they need oxygen, they need nutrients, they need to get rid of carbon dioxide, they need to get rid of their waste products. And they do that by connecting to these vessels that are here in the central canal through those little tiny thread-like tunnels called canaliculi that we talked about last time. So the lacunae are all connected together by these thin little tubes, and then those tubes connect to this central canal so that they can get their nutrients and get rid of their waste products. All right. So in the osteon, we have these concentric lamellae. A lamellae is just a layer. So lamellae is like strata. You know, strata is a layer. Well, a lamellae is also a layer, or a level. So osteons are arranged with these concentric lamellae. So what does that mean? Concentric just means sharing a common center. So we have this tube of bone on the inside, and then the next lamellae wraps around it, the next lamellae wraps around that, and so on. So we have this kind of bullseye shape if we look at these in cross-section, where we have a center that has the vessels in it, and then we have these concentric rings around it that are these concentric lamellae. Now, the collagen fibers in these concentric lamellae are actually arranged in, they're perpendicular to each other. So, you know, if we have a tube like this, the collagen fibers on this tube will be like this, let's say, and then the tube, the outermost tube, or the next one out, not an artist, but the fibers in this one will run the opposite direction. So it gives bone additional strength, because it means that as you look through the osteon, you have a crisscrossing pattern of those collagen fibers, which means that this osteon is not going to bend as much this way or this way, because all those fibers are perpendicular to each other. All right. And in compact bone, the osteons are arranged parallel to the force that's going through them. So if we have a long bone here like this, and you know we've got force that's going through the bone, and it goes through the middle, right? So the osteons are arranged parallel to that. So like here's a drinking straw or an osteon, and so on. So what that means is, just like, you know, if you took a bundle of drinking straws and you set them on the table, you know, tall ways, and you went to push on the top, those drinking straws are not going to give way very easily, because they're, you know, all of their strength is in their tall side. Now, if you took that same bundle and you pushed on it from the side, you could probably get them to bend. And compact bone does the same thing. When forces are running parallel to it, there's very little compression. You know, osteons are very strong. They won't collapse or crush. They hold their shape. But if you push on it from the side, they will bend, because they are not as strong from the side as they are in their long direction. So we see compact bone where forces are coming all in one direction, and we see injuries to compact bone when forces come in from the side or perpendicular. So oftentimes, you know, bad breaks to the arms and legs happen when forces come in from the side, because the bone is not as strong in that direction as it is in its normal use of transmitting force down and through.
So in each of the straws within the straws, all the collagen fibers are going the opposite direction.
Right, they go opposite directions. Okay. Each level is will be perpendicular to the one next to it. All right, so the arrangement here is we have these osteons that are all clustered together, and then on the inside we have an open space. That's the marrow cavity, and then surrounding these the cluster of drinking straws, or the osteons, we have a long, or a lamellae that goes all the way around, and we call those the circumferential lamellae. So like if here's an osteon and here's one, surrounding all of the osteons together is kind of a giant version of an osteon that goes all the way around that bone. So we call that the circumferential, just means to go around. Lamellae is layer. So this is the layer that goes all the way around all of those different osteons. All right. Do I remember everything I wanted? I think so. Okay. So then the other kind of bone is spongy bone. And here what we're looking at, this is the femur that we've cut in half. So we're looking, we cut it long ways so that we can look into the head of the femur. And you can see down here how this is almost tube-like. Well, this is compact bone, which you often find in the diaphysis, or the shaft part. But up here in the epiphysis, we don't see, we see spongy bone instead. So you can, if you look carefully, and you'll be able to see this in lab when we get to the skeleton in a couple of weeks, there are all these little holes in spongy bone, which is how it got its name. A sea sponge, if you cut it in half, you'll see all of these little holes inside. So spongy bone got its name because it looks just like that. But it's not fair to say that spongy bone is spongy. It is sponge-like in appearance, but it's actually very rigid and strong. So don't think that because it has that word spongy in it that it's somehow soft. It's not. And spongy bone is created by these complex three-dimensional scaffolds that we call trabeculi. So again, it's hard to depict the three-dimensional thing in a two-dimensional picture, but this is sort of what spongy bone looks like close in. We have all of these interlocking, interconnected trabeculi that create a scaffolding that's very rigid, but it also has spaces in it. So here's a space, here's a space, here's another. Now, if we look inside these trabeculi, we see an organization that is sort of like an osteon. We still have concentric lamellae here, but we don't have the same rigid organization that we have in compact bone. Some of these trabeculi will have a central canal. Most of them won't, because spongy bone usually gets its nutrients from the spaces here that have blood flowing through them all the time. So it's a little bit of a looser structure, but you still see some of the same patterns. So concentric lamellae, but not that same, rigid organization. All right. So we don't see osteons in spongy bone. Osteons are only found in compact bone. Those concentric cylinders only found there. And spongy bone we see where stresses are arriving in multiple directions. If we look back at our femur here, we have the weight of the body is coming down here like this, right? But then it has to make a bend. It has to turn and then turn again to find itself going down the diaphysis, or the shaft of the bone. So if we were going to arrange our osteons to allow for that transmission of force, there's not really a good way to do that. So instead, what evolved is we'll just fill the space with something hard that will transmit forces in any direction, regardless of how they're going. And that's exactly what we see spongy bone do, is transmitting forces that have to curve or bend or twist somehow, because you have that space filling instead of the compact bone, which doesn't fill very much space, but it's very, very strong. Spongy bone takes up a lot of space, but it's light for its rigidity. All right. So if we were to take just the spongy bone out, this is sort of what that looks like. So you see this complicated three-dimensional scaffolding, and then there's all these spaces in it. Now, in the living bone, these spaces are going to be filled with bone marrow. So you're going to have blood cells in there. You're going to have what we call stem cells, or cells that create blood cells, all sort of locked up in the sponge. So the water in the sponge of spongy bone is bone marrow. Just like your sponge in the bathtub is full of water, well, in bone, it's full of bone marrow and blood instead. All right. So spongy bone reduces the weight of the skeleton significantly. If we took the head of the femur here and we made this all compact bone, it would probably weigh 2 or 3 times as much as the spongy bone does. Because spongy bone is as much empty space, or at least space filled with other things, as it is heavy bone. So it lightens the skeleton, which means that we're able to move faster and be more agile because our skeleton doesn't weigh as much. All right. So we still have all the same players. We have osteocytes in spongy bone, in the lacunae. We still have lamellae. We have osteoblasts, which are cells that are making new bone. And then we have osteoclasts, which are dissolving bone. Now, in flat bones, what you often see is this pattern. It's sort of like a bone sandwich. You know, we have compact bone on the top and bottom, and then we have cancellous or spongy bone in between. And you can imagine that this lightens this bone. If the whole bone were compact like this, no empty spaces, that bone would be much heavier. So in the skull, for example, our skull would probably weigh 2 or 3 times as much if it wasn't for the spongy bone that fills the inner spaces between the compact bone on the top and bottom. All right, so our first question of the day. Spongy bone is which of those things? But I have to send it to you, so give me a second. There we go, multiple choice coming at you right now.
I haven't even looked at it. I just opened my screen.
It's all right. It's all right. I don't have any way of following individual performance, so it's more of a group effort. All right, we're out of time, so jump in there. Okay, big spread on this one. Okay, good. So spongy bone is not very dense. It's actually much less dense than compact bone is, so it's lighter weight for its size. I mean, that's density. How much does a thing weigh for how much space it takes up? So it's not very dense. You can make an argument on concentric lamellae. When you look inside the trabeculae, do you see something that sort of looks like concentric lamellae? Yes, but they're not called that. Only in osteons do you find the concentric lamellae that circle that central canal. Contains interlocking plates called trabeculae. That's really the correct answer. That's the best answer here. Now, do they always look like plates? No. Sometimes they look like, rods or even interconnected tree trunks or tree branches, rather. But the trabeculae are what make up spongy bone. That's the bony part of spongy bone. It has many spaces. Yes, spongy bone does have lots of spaces, but it doesn't lack osteocytes. We still find lacunae with osteocytes in them in spongy bone as well. And then the primary component of compact bone, that's osteons. Osteons are what make up compact bone. Spongy bone and compact bone are sort of the 2 different bone types that are present. All right. In which type of bone would osteons be present? All right, jump in there, last few people. All right, so this isn't a relationship. Osteons are only found in compact bone, nowhere else. So when you hear osteon, you're talking about compact bone. Spongy bone does not have osteons. It has trabeculae. So trabeculae goes with spongy bone. Osteons go with compact bone. All right, and in which type of, we didn't really talk about this, so I'll just talk about it instead. Osteoblasts are cells that make bone, right? Osteoclasts are cells that destroy bone or take bone back up. Both of those cell types are found in both of the types of bone. So spongy bone has osteoblasts and osteoclasts, and compact bone also has osteoblasts and osteoclasts, which makes sense. You know, we talked about last time how bone is always remodeling. You know, bone is always being destroyed, bone is always being made in any given bone. So in order, if that's going to be true, it means that both of the bone types have to have both types of cells, cells that are turning bone back into raw materials, and cells like osteoblasts that are forming new bone all the time. So we see both of those cell types in both. All right. So surrounding every bone is this very important, tough, fibrous tissue layer that we call the periosteum. Peri means around or close to. Osteo means bone. So this is the periosteum, is a tissue that surrounds the bone. So covering every bone in the body is a periosteum. Now this tissue is very tough. It's one of the toughest tissues in the body in terms of its strength. So in most fractures, at least fractures that, broken bones, that don't actually move the bones, in other words, the bones don't become displaced or the ends don't separate, the periosteum is intact even though the bone has broken, which tells you that this tissue is very tough. You know, if it's tougher than the bone it's surrounding, that's a very tough tissue. And periosteum is very important in the recovery from bone injury, because oftentimes the periosteum itself actually holds the bone in position. So even though the bone has been broken in half, the two ends can't move apart because the periosteum is so strong that it's holding that bone back in place, which is what you want to have for that bone to heal. So the periosteum has a number of different functions. One is it's the place where the arteries and veins that are going to supply the bone, or at least the bone on the outside, the outermost parts of the bone. The periosteum has a rich blood supply. That's one of the reasons why in a bone break or a fracture, bleeding is an important part of that process, because when the periosteum is damaged, it bleeds a lot. All right. The periosteum also separates the bone from surrounding tissues. You know, nothing in the body exists in isolation. You know, everything is, all compact in one, organism. So right on top of the bones, you're going to have muscles, you're going to have arteries and veins, you're going to have connective tissue, tendons and ligaments and things like that. So the periosteum separates the bone from whatever is around it, like muscle, for example. The periosteum is important in bone growth, particularly the kind of growth that we call oppositional growth, or when bones get bigger around, the periosteum plays an important role there. The periosteum has a very rich nervous supply, so there are a lot of nerves that run through it, and it's primarily responsible for bone pain. So when a bone is injured, fractured, damaged somehow, or even infected or has a cancer inside it, it's the periosteum that is really responsible for the pain that's experienced with anything that goes wrong with the bone. And one of the and bone pain is particularly difficult to treat. You know, the normal ways we treat pain, like with narcotics or local anesthetic, it's very hard to numb the periosteum. So bone pain can be very difficult for patients to deal with because there's not very good treatment for it. The periosteum is very, very tightly bound to the bone. It's one of the tightest connections between any two tissue types in the body. And the reason for that is on the inside surface, the periosteum has these very tough threads that come out. And they go down into the bone itself. So we call these perforating fibers. So like here's one right here. This fiber is embedded in the bone, but then it comes up and continues, and it becomes embedded in the periosteum too. So it is nearly impossible to peel the periosteum away from the bone that it's covering because of these perforating fibers that are quite literally anchored, usually in compact bone, on the surface or on the outermost part of the bone. So very, very tough fibers that make that connection. All right. So that's on the outside. The periosteum surrounds the outside of the bone. But as we've seen in our pictures, bone is hollow usually. There's some part of the bone that is relatively hollow. So the inside of that hollow space is also lined with an important membrane. This time we call it the endosteum. So endo is inside, osteum is bone, so this is the tissue inside the bone. So endosteum lines the marrow cavity. So, here's our compact bone. Periosteum will be out here, and then lining the inside is the endosteum. And one of the most important cell types that are found in the endosteum is the osteoclast. So those cells that are destroying bone all the time, or turning bone back into calcium and phosphorus and collagen, are usually found in this layer of endosteum. Now, this makes perfect sense. If osteoclasts are going to destroy bone, it makes much more sense to take bone or to dissolve bone from the inside of the bone than it does from the outside. If we were to dissolve bone from the outside, we would change the bone shape. And as we'll see when we start looking at the musculoskeletal system, a bone shape has everything to do with the muscles that affect it. So if we were to change a bone shape from the outside, we would mess up how that bone functions with the muscles that attach to it. So it makes a lot more sense to dissolve bone from the inside than the outside, which is exactly what the body does. So in this endosteum, we see osteoclasts. We also see those osteoprogenitor cells. These are cells that can replace osteocytes and osteoblasts. So again, in a fracture situation where bone tissue has been damaged, we need to replace the cells that have been destroyed. And these osteoprogenitor cells can do that. They can create daughter cells that will become osteoblasts and eventually osteocytes and replace the cells that were lost there. So in that endosteum, the two big players are osteoclast and osteoprogenitor cells. And then we also have osteoblasts are found in this region too. If bone is being taken up from the inside, we have to make sure our bones don't get too weak or brittle. So while the osteoclasts are dissolving bone, the osteoblasts are laying new bone down, just like we talked about last time. All right. So bones grow in three ways. They grow by oppositional growth. Notice the spelling here. This is not oppositional like to oppose a thing. This is oppositional or appositional, which is to make larger around or to build up. So appositional growth, this is how bones get larger in diameter. So bones get thicker and heavier by appositional growth. All right. And then the initial formation of bone, we start as a single cell, but we develop into a human being, and part of that process is to grow a skeleton. So the two ways that the bones of the skeleton are formed is by endochondral ossification and intramembranous ossification. So intramembranous ossification, this is how flat bones form. So these are the bones of the skull, for example, some of the bones of the chest wall, like the ribs and the sternum, all form inside a membrane. So we call that intramembranous, membrane inside a membrane. Ossification, this is bone formation. To ossify is to become hard, is what that word means. And what we'll see is that a substance is first made, and then it's transformed into bone. And that transformation from some other tissue to bone, we call that ossification. So ossification is to turn something into bone. So if we have intramembranous ossification, this is the transformation into bone inside a membrane, which is how the flat bones form. And then the other one is endochondral ossification. So endo is inside, chondros is cartilage. So endochondral is inside of cartilage. So this is the transformation of a tissue into bone that happens inside cartilage. And what we'll see is that most of the bones of the body, all the bones except for the flat bones and the sesamoid bones that form later in life, all of the bones start with a cartilage template. So in development, first the body makes a cartilage piece that looks like a bone, and then that cartilage is transformed into bone. And that's the process by which most of our bones grow. Cartilage template, which is then transformed or replaced by bone, and then that bone continues to grow until we reach adulthood in a kind of endochondral ossification that allows bones to get longer. All right. So in appositional growth, this is sort of the simpler ones. We have osteoprogenitor cells not just in the endosteum on the inside, but we also find them in the periosteum on the outside. Osteoprogenitor cells create osteoblasts. Those osteoblasts sort of line up in a circle around the bone because here's the periosteum, right? It's wrapped all around the bone. Underneath the periosteum is, during appositional growth, a layer of osteoblasts. These osteoblasts are going to make bone, right? So they're going to make bone around themselves. Eventually, they're going to be, locked in position by the bone they've made. Now they're osteocytes and they've made a circumferential lamellae because they started like this. They grew bone on both sides of them, and now we have this pattern instead. So this ring, so to speak, is new growth, these two rings. So you can imagine if this is happening all the way around the bone, well, this bone just got one ring larger. So just like we talk about with trees, every year they add a ring. Well, in appositional growth, bone has just added a ring. So the bone has gotten one ring bigger. And this process can continue, to make the bone thicker and thicker and larger around. Now, over time, there is remodeling. So if we look down here, this is the size of our infant femur, let's say. And because of appositional growth, now it's gotten bigger. So we've gone from this size to this size. But you can see how the marrow cavity hasn't changed size. Well, over time, that wouldn't make sense. Our bones would get thicker and thicker walls, and they'd get heavier and heavier, but not necessarily stronger and stronger, and we don't need them to be that strong. So as the appositional growth occurs, the marrow cavity is also expanded. So first the bone gets a thicker wall, but then the wall gets thinned back out as the marrow cavity is dissolved. So that in the end, we have walls are about the same thickness, but the whole bone is bigger around. So we have this kind of multi-step process where first a new circumferential lamellae is added, but then eventually the osteons in the center are dissolved to expand that marrow cavity. And then the last step is, when we get lots of rings here around the bone, these are not as strong as the smaller osteons all lined up. So as the bone gets bigger, the deepest of the circumferential lamellae, which are here, are actually transformed then into osteons, which are stronger. So, and this doesn't really show you that, but, like this layer right here of osteons on the outside, it was once circumferential lamellae, but the body replaces the deeper circumferential lamellae with osteons because osteons are stronger. So there's this process of bones getting bigger, the marrow cavity gets bigger, and then the innermost circumferential lamellae are replaced with osteons for strength. All right. And let's see, what time is it? Hold on a minute. Where are we at? We can talk about this. All right. The most complicated of the three kinds of growth is this one, and that's endochondral ossification. And what makes it complicated is it's a multi-step process, but it's important because this is how most of the bones in the body form. So first, in the developing fetus, the fetus's first skeleton is made up entirely of cartilage. So a cartilage skeleton forms, and then the individual bones of that cartilage skeleton are then replaced by bone in this process called endochondral ossification. All right. In a sense, this process isn't complete until adulthood, because during childhood, when the bones are growing longer, we just saw how bones get bigger around. Endochondral ossification is how they get longer. And that process occurs at this elongation happens at the growth plate. The growth plate of a bone is also called the metaphysis or the epiphyseal plate. And you will hear people use all three words or all three phrases. So they're good to have all three of them. We already learned the metaphysis is the region between the diaphysis and the epiphysis. Well, it's in that region that we find the growth plate or the epiphyseal plate, which are all sort of the same thing. So in fractures that occur in children, this region is exceedingly important. And since fractures in children are relatively common because children are adventurous and active and have a tendency to, break bones that are smaller and less resistant to fracture than the adult, these come up clinically quite often. Issues with the epiphyseal plate or the growth plate in fractures involving kids, which we'll see when we're going to talk a little bit about fractures next time just for fun, and you'll see some examples of those. All right. So we start with a hyaline cartilage model, and you'll look at hyaline cartilage in lab next week again. Hyaline cartilage is sort of a tough plastic. It's not very rubbery. It's kind of hard and firm and kind of glassy. And this hyaline cartilage model is what forms first. On the inside of this model, as the cartilage model expands, it starts small. It's not like it starts at some particular size. All the bones sort of grow into their original, or into their shape. As the cartilage model gets bigger, the inside of it kind of starts to fall apart. And the reason for that is cartilage is very avascular. It doesn't have very many blood vessels in it. So when you get into as it gets larger, the center of it starts to suffer, so to speak, because it doesn't have a blood supply that can sort of provide for it. So it's in this part of the cartilage that's where the cells are dying and spaces are starting to form, is where the first part of this endochondral ossification happens. So the first thing that happens is along the outside, and this is the epiphysis right here, and this is the diaphysis, along the outside, blood vessels start to form next to that model. And as they do, the periosteum, which has developed around this model, it starts to lay down some initial bone along the outside of the diaphysis. So we haven't really started replacing the cartilage model yet. We've just started adding some bone to the outside. So that's the very first aspect of replacement of this cartilage model with bone is there on the outside. But then in step 3, we get the real beginning of it, and that's a blood vessel invades that cartilage space, that space that has started to fall apart because there's no blood supply. And once that blood vessel starts or invades that space, bone starts to form in that space the cartilage is leaving behind. So we call this first region that starts to ossify or become bone, this is the primary ossification center. And it is going to expand to ossify the entire diaphysis. So the diaphysis is the shaft part. This primary ossification center eventually enlarges to include all of that. And it's at this point that we start seeing a true medullary cavity or marrow cavity on the inside of the bone, where we have an open space. So we're getting sort of starting to look like the final result. And then as the epiphyses get larger, the same thing that happened to the diaphyses starts to happen to them. So the cartilage in the center of the epiphyses kind of starts to fall apart because it doesn't have a very good blood supply. So in step 5, we get invasion of blood vessels into the epiphyses, and now we get our 2 secondary ossification centers. So first, the bone, the cartilage model gets replaced by bone in the center and the diaphysis, and then next is at the epiphysis, or at the epiphyses. So we have 2 primary or secondary ossification centers, and the same process that happens here that happened here. So this ossification center expands and eventually replaces almost all of the epiphyses with cartilage, but not quite. And the not quite part is important, because when we get here to step 6, this is the part that goes on for 16 to 22 years, where the part of the bone is still cartilage, and part of the bone is bone, and as cartilage replaces bone, the bone gets longer, and the epiphyses gets bigger. So when a baby is born, this is sort of what it looks like. We have a big ossified region here. We have, in the epiphyses, a cartilage layer surrounds the whole thing. We call that the articular cartilage. This is the cartilage that allows bone to move against bone nice and smoothly. It's what's affected in certain kinds of arthritis. And then between the epiphyses and the diaphyses, we have this plate of cartilage called the epiphyseal plate, or the growth plate. And as the cartilage cells here divide and grow, the bone gets longer. But as they divide and grow, they're replaced by bone all the time. So as the cartilage grows, the cartilage at the top and bottom get replaced by bone, and that bone continues to get longer until puberty, when the ossification outspeeds the formation of cartilage. So essentially the bone stops growing. All right. And I think we're going to stop there for today, even though we're a little early. I told you sometimes we'd get done early.